All right. So here's the itinerary for the things we're going to go over in this review, and we'll try to get through everything in as quick a time as possible. We're going to start with just a little bit of introduction, and then we're going to go on to our first project, which is our older project, BruinBot, which is in a more advanced stage of completion. Currently has 2 sub-teams working on it, which is mechanical and software. They'll have a chance to get some feedback, and then we're going to move on to our new project, which is ARC, which has the 5 sub-teams of chassis, launcher and reel, electromagnet, controls, and software. So after those teams are done presenting, we'll also have an opportunity to get feedback on ARC teams. And then we're gonna just wrap up the meeting.
So a little bit about X1 if you're unfamiliar with our organization. We're a student-led robotics team under ASME here at UCLA. We don't have a competition each year, so the way we kind of run things is that we choose an original project, so some kind of robot, and we set goals to meet at the end of the year, usually with brainstorming, design, prototyping, and manufacturing, though due to COVID-19 last year, there's been some backlog. But the goal of our organization is to kind of just provide students with a kind of real experience to kind of get some work in a full design cycle. Currently, we have 32 students and we have 3 projects. We'll be presenting 2 of them, but the Guardian is still, or is just wrapping up now. And we have 7 sub-teams in total. So the first project that we'll be sharing with you guys today is the BruinBot. So a little bit about the BruinBot. It's a project brought over from last season of X1. It's a companion robot that's designed to kind of work like the KiwiBot and interact with students across campus. Last year, we finished up design of most subsystems, but this year we really wanted to redesign Payload and kind of integrate all the systems together. And all right, take it away.
Hi, my name is Anthony Chung. I'm a second-year mechanical engineering student working on BruinBot Mechanical. So for our sub-team, we had 2 main goals this quarter. It was to simplify the payload design and adjust the arm design. More specifically for the payload system this quarter, we wanted to create a new design to dispense the granola bar to the robotic hand. The previous system featured unnecessarily complex parts and moving systems to dispense the granola bars. So with our new design, we plan to maximize the reliability of the system by simplifying it. Also, we plan to minimize the size of the payload system to create more available space inside the chassis. And for our arm design this quarter, our more specific goal was to create a system to raise a robotic hand holding the granola bar to a comfortable height for the student to reach. The previous arm design was overly complex and it wasn't consistent with the general aesthetic of the BruinBot. So with our new system, we plan to design a new and simplified robotic hand that serves the same purpose as the previous model. And the shoulder and arm assembly were simplified to serve the same purpose of raising the robotic hand as well.
Hi, my name is Sonika Sethi, and I'm a 3rd-year mechanical engineering major. I will be discussing the payload design for BruinBot. Originally, we had a very complex payload involving stacked granola bars hanging in a compartment attached to the top of the chassis and a pulley system that moves side to side to push out the granola bar onto the conveyor belt. We felt that this was much too complicated and had too many moving parts considering the simple goal of the system, which is just to push the granola bar out onto the belt. Our new system is much more simplified with a lot less moving parts and is very similar to a vending machine, and it includes 4 compartments with coils connected to motors. This new design also takes up considerably less space than the original design. When selected by the user, the granola bar of their choice will be pushed out onto the belt by the rotating coil and slid out onto the hand to deliver to the user. Restocking is also simpler now. We moved the door opening from the side next to the arm to the back panel and attached drawer sliders to the bottom of the carriage for easy removal. In our new design, 5 to 6 bars will fit per compartment based on the pitch of the spring, so around 20 to 24 bars total. And while this is possibly less than the original payload design due to the less compact storage of the bars, this is still a pretty good number of granola bars. And some possible future additions include maybe adding a funnel to orient the bars when they land on the conveyor belt.
All right, cool. Thanks, Sonika. So my name's Zach. I'm a third-year mechie, and I'm the sub-team lead for BruinBot Mechanical. And I'll be going over the arm redesign. So our main goal with this subsystem was to create an arm that would be able to keep the candy bar level while delivering it to the student. To accomplish this goal, we were inspired by parallel linkage mechanisms using 2 fixed pivots in the shoulder joint connected to 2 aluminum bars that make up the internal structure of the arm. As you can see, as the arm moves, the hand remains parallel with the ground. We thought this was a very simple and effective way to carry the item. And also, last year's design utilized an optical encoder to monitor the position of the motor. And we've replaced this with a simple limit switch just in the shoulder joint because we felt that an optical encoder was a bit overkill since realistically the arm only has a lowered and raised position. In terms of aesthetic improvements, we've aimed for a less lanky design. We've tried to keep it more consistent with the overall look of the robot, so more round and geometric shapes. And the sleeve design is still in its very early stages, and we plan on refining this in the future. Finally, while only one arm actually moves, we plan to mirror this assembly just for symmetry's sake, but we only plan to have one motorized arm. Yeah, speaking of motors, these are just some of the simple calculations we went through to verify that our design is sound. So the motor that we're using is a 775 Pro, which is the same motor as last year. A quick search will tell us that the stall torque is about 0.52 foot-pounds. Used in conjunction with the 10-to-1 gearbox, our total torque limit is going to be about 5.2 foot-pounds. Next, we can approximate our whole arm assembly as a point mass acting at its center of mass, which is located about 15.7 inches from the motor shaft. We can then approximate our arm assembly as about 0.8 pounds and the arm sleeves as about 0.5 pounds using SolidWorks mass properties. This corresponds to a torque of about 1.7 foot-pounds on the motor shaft, which is well below the acceptable limits. This is kind of expected since I'm assuming a similar calculation was done last year, but their arm assembly was actually much heavier than ours, so it was still a good sanity check just to make sure that our design should work. We also investigated possible failure modes for the gearbox shown in the top right. But we see that these torque values are much higher, so they'll probably not be the limiting factor for us. And overall, we don't anticipate any issues here since our assembly is pretty light and there's not a whole lot of external forces that we have to consider. And just to wrap up BruinBot Mechanical, I thought it'd be helpful to see like an overall comparison between the old and the current design. So the old on the left here and the current on the right. And even though we still have room for improvement, hopefully you agree that we're at least moving in the right direction in terms of our main goals of simplification, reliability, ease of manufacturing, and ease of long-term maintainability. And yeah, that'll wrap up the BruinBot Mechanical team. So now I'll just let Rebecca talk a little bit about the prototypes that she's been working on.
Yeah, so here's just a quick demonstration. I got a 3D printer recently, so I decided to print off a prototype of the head design. And this is a design that I worked on last spring. So a couple screenshots of the cat are shown in the photos there, so you can see all the components put in place, including the driving gear and the main axes that's the whole head assembly is gonna hang off of. But I just printed this outer shell. It's designed to be printed and then have acrylic panels covering up some of those gaps. The LED faceplate will be mounted on one of the panels on the front. So hopefully this is just goes to show that a lot of parts of this assembly are absolutely ready to be manufactured, and we're just taking extra time since we don't have manufacturing capability right now.
All right, so hey everyone, I'm Nikhil. I'm the sub-team lead for BruinBot software, and I'm a third-year CS major. So this quarter, we're focused on defining BruinBot and giving it a personality. So the ways we did that was we increased the interactivity with the bot. We implemented voice recognition and voice response from the bot. We also created a graphical user interface on the bot's touchscreen that has easy to understand options and a really clean interface so anyone can interact with the bot anyway. Just a couple next steps going into spring quarter. We're going to be finalizing how the GUI looks and connecting that with the voice implementations, connecting the face display that Rebecca made to the whole like bot's brain and the voice recognition, and then updating our last year's image recognition software so the bot can identify different objects, and creating new commands that you can talk to with BruinBot. So as for the voice recognition and response, so the way we implemented it is we use Python speech recognition, which is our speech to text module, so you can talk to it. We use PyTTSX3 to convert that text to speech, so we can alter the voice and give BruinBot a little character to it. The way we analyze what the correct response should be is we use keyword analysis on the text to figure out what the person is asking and how the bot should appropriately respond. So a couple commands that you can ask BruinBot. You can ask what the weather is and it'll give you the weather in Westwood. You can ask for a joke. You can ask it to do a dance. You can say bye. You can ask who it is. You can ask it to sing. You can ask it to play music. You can ask how old it is. You can tell it to give you a fun fact about UCLA. And you can even play a fun guessing game with it.
I'm Ryan. I'm also on the BruinBot software team along with Nikhil. I'm gonna go over the graphic user interface we created for BruinBot. So basically, we're creating a graphic user interface that's gonna go on a tablet in the front of BruinBot, which is gonna be how users interact and it's connected to the stuff Nikhil was talking about with the voice recognition and response. Basically, you can see it on the side right there. There's the middle button, which allows you to speak to BruinBot and then ask for the commands that he was going through, as well as green buttons on the top and the bottom, which are just like direct commands. So you wouldn't have to talk to BruinBot. It would just for example, the top one says, "Who are you?" It would just directly ask BruinBot that command and BruinBot would respond to that in case you didn't want to talk to it and you thought that'd be easier. We're focused on creating a clear and simple interface, as you can see, just so that it's people don't get confused and people will want to interact with the robot. And then when we were designing it, we initially had problems with fitting everything on screen at once since we had so many commands. But we eventually decided that the top 3 commands are the ones we thought were most important or fun for users. So those ones are always there. And the bottom 3 commands are random each time you interact with the robot and just pulled from the rest of the commands that BruinBot has. And obviously the middle button is just to speak to it. And we've got a demo on this, just going through some of the commands that we'll show at the end. These are the BruinBot face emotion animations that Rebecca created over the summer. And then as Nikhil was saying earlier, our focus for next quarter is just going to be to connect these to the work we've been doing, based on the commands BruinBot says or responds to, it could have different emotions. And this is our video demo, demonstrates the commands.
Rebecca, I think your audio might not be shared.
It was working earlier. Can you try unmuting?
Sorry, I couldn't figure out how to unmute myself. I tested this with Kenneth earlier and it worked. So you guys aren't hearing the audio? No.
Try playing it once more.
Share computer sound. Let's try that. Don't know why it didn't work before.
I am BruinBot. I am immortal.
There we go.
Pleased to meet you. Here is a joke. I couldn't figure out how the seatbelt worked. Then it just clicked. I am 92 years old. UCLA is 101 years old. Let's play a game. I'm thinking of a number from 1 to 10. See if you can guess it.
Is it 5?
My number is less than 5. I'll give you one more guess.
Is it 3?
Sorry, I was thinking of the number 4. Better luck next time.
What's the weather like?
In Los Angeles, it is currently 62.58 degrees Fahrenheit.
Play music.
This is one of my favorite songs. I hope you enjoy.
All right, that's enough of that. It does go on for about another 30 seconds, but in the interest of time, we'll cut that one a little short. Yeah, so that demonstrates some of the functions.
I hope you guys like the song.
Yeah.
Okay, so for the next steps that we're planning on taking with the BruinBot on the mechanical side is to finalize the CAD and really flesh out the small details like the fasteners we're going to use and the parts that we might need to order, as well as redesign some aesthetics that Zach and his team might see fit. We're also planning on prototyping the payload assembly just through 3D printing it. On the software side, we gotta integrate behavior code between subsystems. So between drivetrain and payload, for example. We're also going to plan on finalization of the UI code. So implementing the face animations that Rebecca made onto the touchscreen and touching up on the GUI. And overall, just manufacturing and assembling the robot. But this is dependent on the facilities that are available to us in the next quarter or next year. Are there any questions for the BruinBot?
Yeah, can you go in a little bit more detail about your motors that you're using to drive the arm?
Yeah, so it's just a 775 Pro motor. It's the same motor that they ordered from last year that we just decided to go with because it already came to the lab. So just to save on costs.
And how are you controlling it?
I'm actually not too familiar with the details, but I'm assuming there's some kind of motor controller associated. I think it's just a standard DC motor.
So if you're going to be doing that, you're going to need some kind of a PWM-based controller that can talk to your position sensor and have feedback. Were you able to successfully implement a shoulder motor like this last year, or? Pixie.
No, I don't believe any of these components have been manufactured yet. Just the parts have arrived at the lab. So we were planning on doing some more testing with that once we were able to get access to the lab.
Yeah.
So you.
Sorry.
Oh, sorry.
Last year we had.
Oh, so it's gonna.
Last year we had a lot more students dedicated to the BruinBot project. We had a team dedicated to controls, and they worked out a lot of the details for motor controllers. So we have notes on a lot of that, but for this year we didn't have really enough that they could be working on. So we don't have students who are currently working on that, but when we are assembling everything, hopefully we'll be able to do a lot more testing and get some of that knowledge back integrated into the system.
Okay, so for what it's worth, 775 size DC motor, commutated DC motors in general are not really suitable for robotic motion control. I was going to say that if you had prior experience where someone had managed to make it work from a year before, then maybe, maybe I'm wrong here, but for what you're trying to do, I would assert that probably a stepper motor is closer to what you want. And the associated stepper motor controller, because those are made to move to specific positions and then stop, rather than run at a constant speed, which is what a more typical commutated DC brush motor would do. I'm not saying it can't be done, but you're going to have to do a lot of the interface between the sensors, the position sensor, and the PWM controller than you would probably think you would otherwise have to do. And you would definitely need an encoder to manage the position and acceleration of the motor. You would not be able to accurately do it with just a limit switch.
Yeah. Sorry.
This motor was chosen or just brought over from last year, but definitely the benefits of a stepper motor might be more suitable.
So, and again, if you've been able to make it work in prior years, then or if you had a way to make it work that was known in advance, I'd say by all means go for it. Like if, for example, your 775 was geared down to rotate at a super slow speed, such that it could be stopped by a limit switch, then maybe that would be appropriate. But yeah, I don't know. Just I've got no experience with the BruinBot before, so this is just my gut feeling.
Yeah, I'm actually really glad you brought that up, because this is probably like the biggest point of confusion for me. And actually very early on in the project, I was looking at like geared NEMA 17 stepper motors, just because that's what I was more familiar with. But we ultimately just decided to trust the call made by the team last year and just use the motor that was already ordered. But it's definitely something to look into. So yeah, thank you for the input.
Yeah, I can kind of clarify this. So the 775 is a legacy from last year's team, and it was chosen because we needed the high torque application, since we were doing a essentially like a two-link system where the forearm and the bicep kind of flexed independently of each other, but were controlled by one motor. So that's why we went with this stepper, or we went with this instead of a stepper. And one of our EE guys swore by it because he had worked with it with FRC. It's interfacing with an Arduino, so that's what's giving it the PWM. But I do agree that if you plan on getting rid of the encoder and making the arm lighter, definitely switch to a stepper and give that thing a limit switch, and that should give you what you want. I agree.
Yeah, these are definitely things to revisit. I mean, this part's been on the shelf for this entire year, and we've had no work with it at all. So yeah, that is a good thing to check out.
Any other questions for the BruinBot? Or comments? Anything you guys might have observed?
Can you go back to that slide with the showing the vending machine body? Okay, what was the design change for the hand? Like what's like what changed for the that plate?
You said the hand.
Oh yeah, like what was it before, and then why did you change it to this?
Before it was like a 5-fingered like humanoid kind of hand, and I think we kind of all agreed that it was a little like uncanny for a friendly robot to have like a human hand. So we just kind of wanted to simplify that. So the current one we have on the right, it's still not super finalized. We still have some improvements we want to make to it, but overall it's just supposed to serve like a tray for the candy bar to land in as it moves upwards.
Okay, because I was wondering if there was like a function to like the fingers, but you know, if a tray works, like I think that's a lot simpler.
Yeah, last year there was definitely a lot more planned for the hand. like to give a fist bump, but we decided to simplify things just to keep it more aesthetically pleasing. Also, we switched the arm from like a 2-bar linkage to just one straight bar.
Random thought that I had was, at least in senior design, we used stepper motors. We kind of just used ones that were laying around in the ASME lab. So I know where you guys are coming from, and it's actually really good to be able to just try things and learn things, because honestly, sometimes data's not there. So I think it's a good effort so far. One thought that I had was steppers do tend to have lower torque when compared to other types of motors. So if you happen to, like, I don't know, just grab one that's in the ASME lab and you find that it doesn't have enough torque, maybe you can buy gearboxes that you can kind of just slap on there. It'll like lower how quickly it turns, but at least it'll match the torque. So yeah, just a random piece of advice.
All right. On the interest of time, I think we should move on to the ARC.
All right, so I'm going to introduce ARC. ARC is our main project for this year. It's a new project that we started at the beginning of this academic year, so it's all still in design and conceptual stages. But here's a bit of an overview of what we want, or what we envision for ARC. If you weren't at our last design review where we talked about a little bit of this, it was actually pitched based on a device called the ODM gear from the series Attack on Titan. And it was modified. So the main goal of the robot is to navigate by walking on a ceiling. So it's hanging off a ceiling by use of electromagnets, and then it's going to be able to calculate and aim and launch electromagnets at the ceiling in order to move with this walking kind of motion. So we have a lot of the design finished at this point. It's a challenging project. It's more challenging than BruinBot because of how tightly everything's integrated. As you can see in that CAD a little bit, everything's in very close quarters. So we're going to be going over a lot of the progress that was done, which is completing the CAD. We've selected electronics. We've done a lot of sort of experimentation with simulation of different aspects of the robot. And then a little bit of physical testing with the electromagnet. So, all right, here is an assembly level draft. This was completed shortly after our previous design review. So this is taking a lot of the feedback together with the conceptual designs from the different sub-teams. So I created this design to sort of put all of it together and give the teams a layout of where things are going to be positioned more or less. There's a lot of notes on this that people incorporated into their designs. And with that came a bunch of parameters, which is something we didn't have previously. So that was a really good step to get some sort of dimensions, weights, sizes, and different information about the parameters of the system. So let's move into the different teams. Please try to move through this fairly quickly if you can, because there are a lot of slides.
Hey guys, my name's Nick and I'm the chassis lead for ARC, and I just want to give a quick overview. So based on the fall design review feedback, we decided to go with the picnic basket design, which essentially, if you weren't there, you can see how there's two arms that can independently rotate from the rest of the robot. And we chose this design versus the other ones because it allows for the least amount of inertia to be rotated with the arm. So it's better for the dynamics of the robot, as stated in the first goal of our 3. And then the other 2 goals are basically just to integrate for all the other sub-team parts as compactly as possible, because you can see this robot's kind of getting big. And the third goal is to make sure that it's rigid enough for the dynamic load so that the controls team don't have to worry about any problems with their controls. And then that's basically the overview. So I'll hand it off to Susan, who will be talking about our frame.
Hi guys, my name is Susan and I am also a 3rd-year mechanical engineer. So the frame is going to be the highlighted portion of the chassis. It's shown on the right. It's composed of 6 parts and they're mounted through L brackets. And total, it's going to be 3.78 pounds, and it's going to be made of acrylic and ABS plastic. So some of the main functions and the main interactions of note are one, that it supports the main axle and houses the electronics. So right now in the red box, you see that that's the main axle, and there's 3 points of contact on either end and in the middle. That kind of gives the chassis structure. And on the bottom plate at the end of the chassis is where the electronics are going to be mounted. The click. The second function is to mount the motor for the arms. So this is the thing that drives the rotation of the arms. It's going to be mounted directly onto the side triangular walls through screws. And if you click again, third function is to mount the gearbox and the motor for the reel. So the reel and gearbox are kind of components that are part of the axle, but to kind of lock it in place so it doesn't shift around when the robot is in operation, we kind of lock it down using those vertical supports that kind of grab on and make sure it doesn't move. And then lastly, if you click again, final function is to connect the wire from the axle to battery. So that middle column also serves as kind of like an avenue so that the wire can travel down and connect to the battery at the end. And to kind of elaborate on that wire pathway, click to the next slide. So on the right, in the red is where the wire would be. So starting from the top, the wire pathway is basically at the top, the wire is encased in a cable and it's threaded through the launcher system and out the bottom of the launcher arm through a hole. And then it wraps around the reel, and the reel is kind of the thing that controls the feed. And then within the reel, the current carrying wire will exit from the reel through a hole in the axle. At this point, it's going to travel axially towards the middle column. It's going to pass through a slip ring until it enters the middle column. And then once it enters that middle column, it's going to exit on a hole at the top of the middle column. It's going to exit through a hole to the outside, and then it's going to trace down onto the bottom of the chassis and connect to the battery where the rest of the electronics are mounted. And next slide. So an important load-bearing component are the L brackets, because it's basically the part that kind of connects everything. So here's a quick FEA data from the L brackets. So displayed are the strain and factor of safety plots on the left. As for a summary, the L brackets are going to be made of ABS plastic. It'll have a yield strength of 45 megapascals. And in these FEA plots, there was an applied load of 10 pounds. And so in summary, it resulted in a maximum stress of 14 megapascals, which is under our yield strength, a maximum displacement of 9.07 micrometers, which is reasonably low, and a minimum factor of safety of 3.1. And then on the right, you can see kind of visually how it's mounted. On the top is an exploded view. On the bottom, you can kind of see what it looks like at the end. Yeah, next slide. And these two are one of the main like structuring components of the frame. So on the left, you can see in reference to the rest of the chassis on the little image on the top, it's the highlighted portion. On the left is that triangular part. It's going to be made of acrylic and it has a yield strength of 45 megapascals. As a summary, it has a maximum stress of 4.5 megapascals, which is lower than yield strength, maximum displacement of 0.5 millimeters, and a maximum strain of 1.7 to the negative third, and a minimum factor of safety of 10. And then on the right is that middle column that I talked about before that kind of provides that pathway for the wire and also holds up and structures the axle. So that's going to be made of ABS plastic. It's going to have a yield strength of 45 megapascals, a maximum stress of 0.28, and a maximum displacement of 9.6 to negative 3 millimeters, and then a maximum strain of 1.7. And as you can see through the plots, there aren't any particular areas of super concentrated stress and strain. So yeah, those are basically the main components of the frame. Now I'm going to pass it along to Riley to talk about the axle.
Hi, my name is Riley. I'm a 3rd-year mechanical engineer. I worked mostly on the axle. If you're at our previous design review, you know that I talked about like broken and connected axle designs. Oh no, that wasn't the last one. I was just trying to figure out how to make the axle in the middle. That was the main problem. That was our own intro design review. Sorry, but for my part, mostly we're going to be talking about the part highlighted in blue. As Susan mentioned before, though, the axle is the entire part in red. However, the rest of the axle is just a hex shaft that we covered in the reel and launcher systems when they talk about how everything's connected there. So next slide, please. So what you're looking at in that blue part is essentially what you see on the bottom. I have exploded and collapsed view just to help you visually see it better. The gray part is a slip ring. If you're not familiar with that, that allows a wire to pass through one end, and then that same wire, well, not the same wire, but the same connections to pass through the other end, and then they can independently rotate from each other, so they won't get like twisted up, which is very important for the reel since it would be spinning quite frequently. On top of that, we will have the light gray part, which is the slip ring mount, and then that will be making sure that the slip ring is connected to the middle shaft, as you can see in the top right. Sorry, I'm moving eyes around a lot. But then those are anchored by the M5 screws. And then lastly, you have those two ball bearings, which carry the load from the reel to support it from the center. And then for the actual, this is how it interfaces with the reel. So the reel, they'll talk about that later more in the reel and launcher, but that's basically what you're winding the cable up on. So the way it fits onto like the slip ring mount is the blue part. If you look at the bottom left, the blue face is holding those bearings in, so the bearings won't fall off the mount. And then the red face is the cutout section that you can see that allows room for the heads of the screws. So make sure that it won't rotate around that. And there's a little room between that that hole and where the mount is. So there's no contact between the mount and that hole. So all the load is going to be going through the bearings, and that reduces the friction. So hopefully it'll spin better too. And then this is just some preliminary FEA on it. We use 10 pounds. I forgot to put that on there, but it's just 10 pounds force upwards. The whole entire the whole entire robot's supposed to be 10 pounds, just for reference. But typically it should only be 5 pounds at the most, because it'll be split both on one side towards the center, one side to the hex shaft. But we're just going to run with 10 pounds for now, just to make sure that it can withstand any weight that it could get possibly. But you can see from here that the factor safety, which is 10, did not break, or the factor safety minimum is 10, so it did not break, and displacement is not large at all, so we are okay on both ends there, which was one concern we had with 3D printing this part. Yeah. And I'll pass it off, I think it's to Shruti, or I think so, something like that.
Great.
Or Lorenzo, sorry.
Okay. Hello everyone, my name is Lorenzo, and I'm a third year mechanical engineering student, and I mainly worked on designing the arms for the robot. Okay, so for the geometry, so we went with a simple L-shaped design for the arm, so that the launcher can rest on top of the arm. And we also had like a sidewall so that it could rotate about an axis. And we implemented ribs, fillets, and chamfers so we could minimize the displacement caused from the launcher shooting the magnet. And also, I drew in a support from the sidewall to under where the launcher rests, also to help minimize displacement as well. I drew up different designs for the support, like more truss looking designs, but this was most simple, and it weighed the less, and it minimized displacement as much as the other designs as well. And the arms are just wide enough for the launcher assemblies, so we're trying to minimize the weight of the arm as much as we can. So we kept it like the minimum, so the gearbox or anything else wouldn't be hanging over the side of the arm. And then the length of the top face is determined by the center of mass of the chassis, because we wanted the launcher barrel to be directly above the center of the mass of the main chassis body. Okay, so FEA. So I mainly, so the FEA was from the force from the launcher barrel once it shoots the electromagnet, which is around 90 newtons. And I mainly focus on factor safety and displacement, which are the two pictures at the bottom. And we realized that one of the best ways to minimize displacement was to thicken the walls of the arm. But when we thicken the arms of the wall, it also like increased the factor of safety as well. So we tried to come up with like a middle ground where of the thickness, so both the factor of safety and displacement would be at a reasonable value. And I also did FEA for the stress as well, as you see in the top right. And the max stress is way below the yield strength. So it won't seem like it will fail. And another task of mine was to do to keep the center of mass at the geometrical center of the arm assembly. And so most of the mass from the arms is on the above the axle because of the support and the top face, and also because the launcher assembly rests on the top side. So we had to add more weight at the bottom to counteract that weight. So I used steel plates as a counterweight. And to find how much mass I needed to counteract the weight from the top side of the arm, I just used the center of mass equation using coordinates and from like the center of masses of the different parts of the assembly, such as the launcher assembly and the arm itself. And I also found the coordinate, like the location of where the geometrical center is in relative to the axis of the drawing of the assembly. And so, and also for the weight. So the weight coordinate is an approximate coordinate because I didn't know the exact size yet of the weight. So I just knew the general location of it. I knew it had to be below the axle and on the edge, the bottom edge of the arm. So I just picked like a general coordinate for that. And I found also the masses of each of the different parts. And I just used the equation and was able to find mass for one weight. And from there, I just used the density of steel, and I was able to obtain the volume. And the width of the weight was already known. I wanted it to be as wide as the arm. So from there, I just adjusted the thickness and the length of the arm so it'd be enough to fit in the arm and also keep the center of the mass at the geometrical center of the robot. Yeah. I'm going to pass it on to Shruti and Philip for the power generation.
So hi everyone, I'm Shruti, and Philip and I were both third-year mechanical engineers also. We worked on the power generation for the arms. So our main objective was to pivot the arms across the axis of rotation, so the robot can aim at a new point on the ceiling in order to move and scale the wall. We had three main action items. First was to select a motor, then we had to choose a method of rotation, and then we had to mount the motor and the rotation mechanism onto the chassis. So moving into the motor calculations, we had some design parameters and assumptions. I'm just kind of skip through those just for the sake of time. But basically, under a factor of safety of 2, we calculated the necessary torque, angular acceleration, and speed of the motor. And we found that the necessary torque output was around 1.7 Newton meters maximum. So then on the next slide, with the torque and angular quantities found, we were able to narrow our motor selection down to these 3 motors. And between these 3, we decided to choose the one on the left, just because it had a lower cost with a similar maximum torque. And once we had the motors chosen out on the next slide, we decided to go with gear-to-gear contact for a rotation method as opposed to belts or pulleys. And Nick can talk more about these FEAs and gears.
Yeah, so Philip is actually sick, so I'm just going to step in and cover for him. So we went for a smaller T size just for a smoother power transmission through the gears. And we went through, we decided to go on gears rather than pulleys because the belt it would be a lot bigger in terms of, as you can see, the arms are already pretty wide, so we didn't want to make that power transmission even wider for the arms. So the gears are also 1-to-1. You would wonder why, but as Lorenzo mentioned earlier, if we keep the center of mass about the axle, then there should be no moment that counteracts we should be able to rotate the arms freely with almost no torque. But just in case, we added a factor of safety, and that's where how they picked the motor or the servo for the arms. And as you can see here, the max stresses, this will be acrylic gears, by the way. As you can see, the factor of safety are 3.6 and 3.7 for the gear that's going to go on the central shaft, and then the gear that's going to be connected to the servo with a servo horn. And that's about it for chassis. Any questions you can ask us at the end, and then I'll hand it off to Marshall, who's the launch and reel lead.
Really quick, guys. looks like we're quite a little bit behind on schedule. So if you guys could highlight only the most qualitative parts of your slides, that'd be great.
Oh, sorry, never mind.
Okay, yeah, so my name is Marshall. I'm a junior in mechanical engineering. And this is just a quick overview of the launcher slash reel. And you can see on the left, the launcher system is a gearbox, which will drive a gear rack downwards, which will compress a spring. Then when it reaches the partial gear, as you can see in the picture, it will disengage and launch out the electromagnet. On the right is a picture of the reeling mechanism. We also have a gearbox that will just rotate the drum, as the chassis team previously mentioned, to reel back the cable attached onto the electromagnet, so we'll be ready for relaunch. Yeah, so since both of the gearboxes utilize a partial gear design, it was important for us to do a FEA on whether a printed gear with using acrylic would withstand the entire chassis weight on top of it. We simulated the entire force on just one teeth, because that would be the end of engagement for the partial gear. And as you can see, the factor of safety is 2.6 and 2.7 minimum for either using acrylic or plastic, so it's safe. And I'll hand it off to my team members.
Hi, I'm Karina. I'm a third year mechie major. So I worked on the launcher gearbox. First, to determine the gear ratio, we chose the output pinion, which will be meshing with the rack that pulls down the spring. So we chose a 3/4 partial gear for the pinion with a 20mm pitch diameter. And we chose this diameter based on the distance we wanted to compress the spring. And then, so from that, we could calculate the desired output torque, which is just the maximum spring force times the radius of the pinion. And then the motor torque was 1 Newton-meter, so desired gear ratio, but the factor of safety 2 is around 2, which is what we designed for our gear ratio with a 50 and 24 tooth gear. Yeah, so just like running through the design that you can see in the picture super quickly. There are 2 gearbox plates which are 3D printed, connected with spacers, and the motor is attached to the gearbox plate on the left through holes that are drilled into the plate. And then the motor pinion is fixed to the shaft using a set screw, which you can see in the smaller picture there. There's like a portion of the shaft which is flat. And then the bigger gear is fixed in place with a shaft collar, which is on the other side of it, so you can't see it in that image. And then a spacer, which will be 3D printed. So to make sure that the plates would be strong enough and not fail, we did some calculations on the bearing load, which you can see the equations we used there. I'm not going to get into it specifically, but we got a maximum force of 388 newtons, which we use for our FEA. Yeah, so here are the results. So we got a minimum factor of safety of 3.7. Yeah.
Hello, my name is Vivian and I'm a third year aero major, and I'll be talking about the launcher barrel. We've basically split up the design into 2 parts, which is an outer shell as well as an inner spring mechanism. The shell has cutouts, as you can see, first for the rack, for the pinion gear to be on the rack, as well as slots on the side to screw in a long screw that acts as a shaft to prevent the inner piece from flying out of the barrel. Initially, we planned to have the shell just have like a lip on top of the outer shell to keep the inner piece in, but we thought the electromagnet might make that break, so we just have it initially just hit the inner piece instead. As well, we also have the inner piece, which is has the rack connected to it, as well as the spring, which is on the bottom, and it's screwed in on both the inner piece and the outer piece to ensure that it's secure and it won't lose or fall out while we're launching. In the middle, in the CAD, you can see that there's a hole running through the middle of both the inner piece, the outer piece, and the spring, and that's for the cable of the electromagnet to go in. For launcher calculations, I won't go too much into it. Basically, we assumed an initial velocity of 5 meters per second, and we found that the change of angle, the angle of impact, won't change too much from how much we launch it. So we stuck with the initial velocity, and we used that to calculate our spring constant, which is about 13.7 pounds per inches, which is how we chose what spring we were going to use. So we just chose a spring that had a higher spring constant than that. And from that, we also found the force that the spring would inflict, which was around 100 newtons. These are the FEA done on the slot, like the upper edge of the slot, which would take in basically the entire spring force that I calculated in the previous slide. So that's probably the most fragile piece on here. And it got a minimum factor of safety of 3.6. These next two FEAs are done on considering of the electromagnet hitting the barrel. The ones on the left, you can see is having the electromagnet hit the complete top edge of the barrel. And those are fairly low compared to the ones next to it, which is we did a split FEA where it would assume that the electromagnet would have all its force hitting just a top portion of it. And I chose on the side that it would be weaker, which is the side with the window cut out. And we got factors of safety of 73 and 25 respectively, so it should be good. And then I'll pass on to Dylan to talk about the reeling mechanism.
All right, hi, so I'm Dylan, third year Mech-E, and I'm going to talk about the reeling mechanism. So very similar to the way that the launching mechanism works, we have the partial gear design as well. A lot of details, but essentially it allows us to disengage the gearbox from the drum without having to move the gear out of the way using another actuator. It's more mechanically simple, easier to manufacture. But one of the cons that comes with it is that we had to make a gearbox that comes with it. So I'll talk more about that in the next slide. There's a lot of calculations here, but the important part to note is just given the length of the cable that we were expecting and how big the drum was, we were able to find out how many times we'd have to rotate the drum in order to pull the entire pull the entire reel in. And from that, just using a bunch of ratios between the radii of the drum and the gears, we found out that the partial gear, the one that would be driving the gear that turns the reel, would have to output at least 5 Newton meters to keep the robot static. However, the problem that came up with was the maximum torque that we would be able to impart on the motor that we chose was about 1 Newton meter, just from the recommendations on the website. So we did it to design a gearbox with at least a 5-to-1 reduction ratio, which I'll go more into on the next slide. And then the gearbox is very simple. Like what we were using for a lot of the other gear applications, we're going to be doing 3D printed or acrylic gears. I know there's concerns about that. Maybe we'll talk about more of that or figure more about that later. But for right now, we just have this gearbox design. We essentially just have 2 gears, two gear reduction stages, both of which use the same size gears. And in order to get a 5-to-1 reduction ratio overall, we chose each stage to have a 20 to 50 gear ratio, tooth reduction. And that results in an overall reduction of 6.25 to 1 and giving us a factor of safety of 1.25. Next slide, please. So a lot more details about the load analysis, but the important part is just to note that the max force that's going to be applied onto the bearings is 160 newtons. and that was using the FEA that we are going to show on the next slide. The FEA, we meet a couple of, yeah, if you could go to the next slide, please. Thank you. The FEA, the conditions were quite simplified, but essentially we just have the fixed, the plate is fixed on one side, and the bearing load goes parallel to the face of the plate. And running the FEA, we had a minimum stress factor safety of 16, so it gives us quite a bit of room. Yeah, that's about it. And I'll hand it off to Abe.
Hello, everyone. I'm Abe Abraham, first year mechanical engineering. And my part was the real drum. It's quite simple. On the far left, you have an isometric view of the drum just for reference, as it was already covered by a couple of teams. And this drum will be attached to the output gear in the gearbox via Dylan's partial gear. And the drum will be entirely 3D printed using ABS. And the second image is a side view of the drum on the gearbox side. And the cable is kind of represented by the red line drawn here. And the cable would normally be wrapped completely around the surface of the drum, but in this case, it's just drawn tangent to it just for simplicity. And it's important to note that the other side of the drum is exactly the same, except that there's a hole in the middle to allow the bearing from the chassis team to mount inside. And the last view on the right is a section view of the drum, and you can kind of see a 2.5-inch long bolt being driven through the center of the hex shaft just to secure it in place. That bolt was unlikely to experience any major stresses simply because it's just holding it in place. And we can also replace it with a pin if need be. Next slide, please. So the FEA that I ran is pretty simple. It's a fairly worst case scenario where the cable is exactly perpendicular to the surface of the drum. There's no more cable left on the surface of the drum, and that cable is supporting all of its weight, and then also the drum is supporting all of its weight. And 10 pounds is the reference weight that I use for the robot, which is 44.5 Newton force in SI units. And this is applied to the kind of the junction between the surface of the drum and the interior of the drum. So right when the drum is about to make a turn into being clamped down by the plate. And the second parameter is simply that the hex shaft is static, meaning that the motor is doing all of the work to keep the drum in place. And as seen in the factor of safety graph on the top, you can see that the minimum factor of safety is approximately 19. So it has a pretty good margin there. And below, you can see a little bit of stress on the von Mises stress graph below, but nothing approaching even the red or yellow ranges. And it's also important to note that the yield strength of 4.5 newtons per meter squared is more than an order of magnitude away from the top, the very red portion. So already with a very light green, we can definitely expect that the center of the drum will not fail. I'll pass it on to the Electromagnet team.
All right, hello everybody. My name is Matt LeCaire. I am the sub-team lead. I'm a second-year mechanical engineer. So basically, this is our design here, and it's pretty preliminary CAD picture. We have our design, which is a filleted head and a cylindrical body. Basically, the filleted head so that the contact of the electromagnet can accommodate for different striking angles. We have some set parameters, like the length being 4 centimeters, the diameter 4 centimeters, and the length of the cable can be variable. And basically, this design was chosen pretty early in fall quarter because it agrees with the physics behind electromagnets, or that of surrounding a ferromagnetic core in such a way that we can get a magnetic flux to go in a certain direction.
Hi, I'm Jaden. I'm a third year mechie, and for the electromagnet, we just went with a simple three-part design, including the electromagnet itself. So basically we're just fixing the electromagnetic to the outer casing using a metal crossbeam, and we're planning to support the weight of the robot by arranging the cord to put the force on the bottom, of the shell, and keep the force on the paracord rather than putting all the weight onto the wire itself. And then the bottom of the shell is a rounded out design, so it can just distribute the stress more evenly, and then so we can leave more space for the paracord as well as potential controls that the controls team might want to put in. So in the next slide. But the pros of this design is that it's relatively simple to manufacture. We only have one metal part and one 3D printed part and 5 screws. So yeah, and it's lightweight because most of the weight is in the electromagnet, which is around 120 grams. So the weight the weight is relatively light, so it's easier for the launch team to work with. And some of the considerations that we have to make were that this design puts a lot of the stress on the screws, a lot of the stress on the screws and the bottom of the shell, but based on our FEA, that should be relatively stable. And then another consideration is that the electromagnet heats up. So we need to think a bit more about the material we're using for the shell, because there's some considerations for a metal shell that we'll discuss later, and then for plastics, it needs to be heat resistant because some materials will sag because of the heat. And I think I'm gonna kick it back to Matt. So.
Yeah, absolutely. So I had the opportunity this quarter to do some actual empirical testing of my own with one of the copies of the electromagnets we would be choosing to use. And I did some testing for this setup here. We have a given theta, and then I'm pulling the force, and the force sensor is measuring what I'm pulling. You can see a real life example on right there. And I did this with 2 different thicknesses. I did this with a standard sort of kind of thin desk, thin sheet metal. And I also did it with a metal weight plate, like a barbell plate. And so I have some basic results here. And basically, I intend to expand this in the future, but there is some confirmation in these results that our electromagnet is capable of holding things, and perhaps even more than expected in some cases. Yeah, so the lessons that we took away mainly from this, that current is significant, far more than we can get from most standard standalone batteries. I think clocks in around 0.5 amps max. We also know that the electromagnetic fatigue is real. This is something I noticed. If you keep the electromagnet on for significant periods of time, it tends to become less powerful. Just because we suspect this is because resistance is correlated with higher temperatures, of course, and also magnetic permeability has some effect on the core's ability to produce magnetic field. Also, as you may have seen from the last slide, having a larger angle with the that is having a larger angle theta as demonstrated in the slide is not beneficial at all, and we want to really minimize that angle. And the shear stress also, because when the magnet tends to slide, it tends to be in a very precarious situation. It wants to fall off. And again, there's also a heat consideration, right? After testing for around 15 or 20 minutes, you notice the magnet can reach around 55 Celsius or 130 degrees Fahrenheit.
My name is Darren. I'm a second-year mechanical engineer, and I'm going to be going over some of the static FEA that we ran for the electromagnet. And in this slide, you can see just the stress and the displacements that would be caused by putting a force of around 20 pounds directly downwards, perpendicular to the bottom face of the shell. And in terms of stress, our max stress is around 6 times 10 to the 6 for von Mises, I think is how you pronounce it. And then in terms of displacement, we got max displacement that's less than 1 millimeter, as can be shown on the right. It looks a little bit, I guess, worse than it should be on the right because we had a deformation factor of around 98. That's just to show, I guess, a better representation of how the electromagnet actually deforms. And then here, this is sort of the metal cross that we had shown in the previous images. It's going to be the cross that's connecting these shells to the actual electromagnets. And in terms of fixtures, we put the fixtures where each of the screws should be. So within each of the rectangular portions, we put the fixtures, and we also put a fixture at the circle in the center. And in terms of force, again, we added a 20-pound force acting perpendicular downwards on the top face of the cross. And in terms of maximum displacement, we had around less than a micrometer and a factor of safety of around 13, which shows that the cross should be able to hold the 20-pound force that we're expecting the bot to hold. And this piece is made out of aluminum right now. Yeah. And then in terms of the actual shell, we're thinking of making this out of ABS plastic through 3D printing. And again, we had the 20-pound force acting downwards, perpendicular to the bottom face. And then for the fixtures, we put the fixtures where each of the screws should be, which is the 4 holes oriented around the cylindrical portion of the shell. And we had the force acting on the circle going downwards. And in terms of maximum displacement, we had around less than 1 millimeter. And we had a factor of safety of around 3. And this ideally should show that the electromagnet is capable of holding the 20-pound force that we're expecting.
Hello everyone, my name is Suresh Kasashmi. I'm a 3rd-year Mechie, and we have some consideration for next quarter. So we're gonna work closely with the chassis to determine how to fix the electromagnet to the chassis. Also, we're exploring different shell material to use, if we should use a plastic or a metal shell, because there's different considerations where we can concentrate the magnetic field or extend the range of it. Also, we're gonna explore different iterative design for the cross part and perform more FEA, vibration to mimic the collision between the wall and electromagnet.
Okay, hello guys, I'm Hayato. I'm the sub-team lead for controls. And so when we first came up with this project last quarter, we figured that there was going to be 2 main areas of research that we needed to look into aside from motor controls and actuating other components such as electromagnets, which included the oscillation control of the entire body, since this system is basically just a regular pendulum that's going to be swinging all over the place. So we need some way to modulate that. And then also yaw rotation control, since that's going to be the primary way that we're going to determine which direction the robot is going to be moving forward. So, and we covered oscillation control during the fall quarter review. So we're going to be working on, or we're going to show our progress for the yaw rotation control this quarter.
So yeah, as Hayato was just saying, basically we used MATLAB and Simulink to develop sort of our controller. And in this schematic, you can just see the block diagram of the controller itself that we made. You can see there's just a couple of step inputs to model what would basically be what the desired angular orientation that we want the robot to follow. So this, ideally when the robot starts up, it'll pick a 0-degree angle based on where it's facing. And it's always going to want to maintain that angular orientation despite disturbance forces and different swinging that Hayato was describing. We integrated a PID controller, and by tweaking some of those parameters, we could basically tell the body of the robot what angle it always wanted to maintain, despite different swinging forces and things like that. And you can see the results of that in the next slide.
Yeah, so right here you can kind of see how the flywheel is going to be used to kind of control the body. There were obviously some pretty big simplifications we did here just by modeling the robot body itself in a block. And then going forward, to make this more realistic for our model, we're going to adjust it so that it more resembles kind of a ball and socket joint hanging from the ceiling, since this robot is hanging, and then the flywheel would be on the bottom. Another thing that we're going to adjust is kind of play around with the input torques on that motor to be within kind of the specifications of the motor that we will actually be using for the robot.
And I guess I should add that currently, like a lot of the specifications about the actual flywheel is reliant on the entire design of the body. So we currently don't have any CADs of the actual flywheel, I believe, in any of the full assemblies. So if someone's wondering about that. And in addition to that, we were also working on just figuring out all of the components of the electronics that we're going to be using this quarter. So I won't go into the specifics for these, but I guess one of the things that we looked into was how to detect when the electromagnet actually hits and makes contact with the ceiling. We basically had a bunch of like brainstorming sessions to try and figure out what the best method would be. And I believe we just settled on using the IMU that would be on board to detect whenever we pull in the wire using the reel, whether or not the entire body moves or not, to determine whether or not the electromagnet makes contact and attaches to the ceiling. And yeah.
Hi, I'm Roger, and then I worked mostly with figuring out the IMU. So what we realized is that it's important to have orientation control for the robot in order to supplement like the yaw control, because if we don't know which way the robot's pointing, then we don't know how to correct for it or how to like properly point the robot so that it can like launch the next reel. And then with the IMU that we decide to go with, it comes with an accelerometer, gyroscope, and magnetometer, which gives it 9 degrees of freedom. But then like individually, the values that you get from each of these sensors doesn't really help you figure out the orientation because it's just like a list of values. So what we have to do is like put it through sensor fusion to basically output like a vector of orientation. And so yeah, how this works is like on the previous slide, we mentioned that we'd be using Raspberry Pi and Python, mostly because that was just that had libraries readily available for the 9250 that we are planning to use. And then next slide, please. So before we jumped all in onto using the IMU and the accelerometer, we wanted to have a proof of concept. So just like scrounging up some spare parts that we had laying around, we found like an IMU that's like has 6 degrees of freedom. We hooked that up to Pi 0, and then ran the code using like the Python libraries, and then basically it output this like roll and pitch, as you can see. Yaw is NaN because it's missing a magnetometer, but this is the position vector or the orientation vector for an IMU that's like basically sitting flat on the table. So you can see that like it's more or less working. And then we'll continue implementing this in the coming quarter.
Right. And in general, for next quarter, we will most likely be getting all of our components, electronic components. So then we'll be testing those out. Thank you.
Hey, I'm Anirudh. I'm the software lead, and I'm a graduate student for studying CS. And so for software, for ARC, we divide into 2 sections. One is like the website, and another is simulation for now. And for the website, we are essentially creating a dashboard with a live video feed and a GUI to operate the ARC robot when we like eventually get it to like go. And so we were able to completely finish the website and have a GUI. I don't have the demo of it just up yet, but we're gonna have the website like live on GitHub eventually, and it's gonna have a live video feed. And that live video feed can take a video from like a Raspberry Pi and just show it on the website. And yeah, next slide. I'm gonna talk about the simulation, or I'm gonna pass it off to Michael. Who's gonna talk about the simulation now.
Michael, I'm a 3rd year Mechie. I worked on simulation with Bradley. So first we created a simple spring-loaded launching mechanism with a magnetic projectile and WeBots. And then Bradley wrote a simple script to model stages of the launching mechanism. So that's in the left image, and the right image was the import of some of the assembly to WeBots, which brings us to our next slide. WeBots we found was kind of limited. So for example, it didn't have the capabilities of simulating all the stuff we wanted to do with EM forces. And when you tried to import a mesh, it didn't import the whole assembly. So it didn't preserve mates in SolidWorks. So you had to go back in and use their kind of mating system to recreate assemblies. So we're currently researching Gazebo and Compelia as simulation options, and we have a video of Gazebo here.
This is simulating a magnet. It's not super clear. Yeah, so like there's like the white magnet that's like being controlled, and there's like a smaller gray magnet that gets affected based on the like position of the magnet. And this is like a more close visualization and like simulation of a magnet, and this is like close to what we want. So like we already have this part kind of ready to go. So we just have to kind of like move over the launching mechanism that we already have built in WeBots. So basically next step is to like port it and then use the magnet connective sets available in Gazebo and Compelia to build out the electromagnet simulation. So here you can see like it's moving based on like the rotation and like all of the different movement of the white magnet. And that's like our next goal with using Gazebo as our like new simulation software. Yeah, that's it. Next slide.
All right, so that's the end of the team presentations for ARC. We're going to open up to questions and feedback based on any of the things that you've seen from the teams.
I have a question. My question is, how are you going to power this electrically?
I guess that would probably be mainly
because it doesn't seem like you have
right?
weight for a battery.
Right. So currently, I don't think should we say that we're not thinking about using a battery currently, and then just thinking about just using a tether to power it, since we were concerned about the weight of the robot.
It seems like that might be the way to go.
Right.
If you are going to have a tether, you're going to have to figure out a power supply for to go on the tether. Just something to think about. And then also, if you're going to have a tether, you might consider also tethering other things. Like obviously you need the sensors to be on the robot, but you might not need the brains. If you're concerned about weight, you could have whatever controller you're going to have not on the robot and just use a long cable for it. That might be a bit of a pain, but it might save a little bit of weight. My other piece of feedback is I hate L brackets. But I think they're okay in this situation. What I suggest that you do though is, I remember seeing on the chassis there you had two parts. One, you basically had like a beam that went into the frame, and then you had and then you had this one. This one I think is fine because the beam goes all the way through the frame and there's a hole for it in there. The base I'm much more worried about. I would suggest doing something similar. So you put holes in the bottom of those trapezoidal pieces and make little slots in the ends of your base so that they can slot in there like you have those horizontal supports. I think that will make that piece a lot stronger. Because it's now, right now, although you did the FEA and showed that it could work, I'm kind of skeptical about a lot of the, this force. It seems a little bit low. I'm not entirely sure how to fix it exactly, but I think that there's a couple of ways you could make it a bit stronger. And putting tabs on the end of the end of that bottom plate and into the sides would make that part stronger at least.
So are you suggesting we put a large slot at the very bottom of the triangular side frame? Is that, I'm a little confused that way.
Yeah, it doesn't need to be one. You could do two.
Okay.
But yeah, so so as you have those long beams insert into the sides, have like tabs on your base insert into the sides.
Okay, for sure. Yeah, we can consider that.
And then you could also do that with the center. You could also do that with the center where it goes into a hole instead of just a mating flat there. It's going to put it's going to put more of the force on the plastic and less on the screws and those little L brackets.
Okay, yeah. I mean, we were just kind of worried about the whole assembly process because the chassis itself is already very assembly heavy and complicated. So we wanted to make sure that like a lot of the parts weren't just like very heavily like based on slots and stuff. So that there's like alignment issues.
I think you'll actually have an easier time if there are slots with things like alignment than if there aren't, because you can't really re-drill these holes. They're so small. Also using things like, because these are going to be laser cut. If you're going to laser cut them, you won't have issues with those things like that. If you leave it a little bit of wiggle room, you can fill them up with things like glue and whatnot. That should be okay.
Okay, then for sure then assembly isn't an issue.
It's not like it's going to make it impossible to assemble. It might take a little bit more time, but I don't think that really should be a concern.
Okay, awesome. Thanks for the tip.
Yeah, thank you, Jacob.
Hey, so I noticed some acrylic being thrown around in this assembly. I think someone already brought up not recommending using acrylic for gears, which I also agree with. They're pretty prone to shattering, at least in my past experience. I also noticed acrylic on these kind of side plates, and you know, like acrylic is generally better as an aesthetic, not a structural piece. I'm not sure if the impact resistance is something you care about. I don't know if this robot would ever like fall off the ceiling or something. But generally acrylic, I think it's like 15 times more impact resistance than glass. But something like Lexan or polycarbonate would be 200 times more. So just something to consider. I know, I'm guessing you guys are gonna laser cut the acrylic. You wouldn't be able to do that with polycarb, but I think you guys have access to a water jet, if I'm not mistaken. So I would just think about maybe the material choice, at least as structural pieces, because it just seems like it's carrying a lot of load.
Okay, yeah, for sure. If it's within our budget, we'll consider it.
Hey, I actually have some stuff to say about the plastic gears as well. I touched on this when I was reviewing the underwater robotics project, but 3D printing your gears laser cutting your gears, you're going to run into problems because the laser will melt. That's how it works. It melts the plastic, and so it's going to tend to round off or otherwise blur or melt the tooth profile, especially with teeth as fine as what you have here. And you're going to have to consider the kerf of the laser cut when that's being done. Now, if you were to 3D print it, you should note that 3D printers typically produce parts that are slightly oversized in the cross section. So you would need to actually shrink the faces away from, or shrink the gear teeth away. Otherwise, they're going to end up interfering when you put them what you think is supposed to be their nominal distance. Those teeth are really, really fine. So I doubt you're going to be able to 3D print them and have them come out accurately. And if you laser them, I would be very suspicious that a laser would be able to reproduce those teeth accurately as well. That's the sort of thing where you may be better off buying blank gears or gear stock, which I've touched on this with other groups, where you can basically buy what amounts to a rod that's got the gear teeth cut into it, and then just slice off gears like you're slicing bread off a loaf of bread. The disadvantage to that is that you're more limited with the number of teeth you can choose.
Yeah, I definitely get what you're saying. I think in my experience working with 3D printed gears in a gearbox, we did have to undersize them. But I think given like with our current budget, it's not possible for us to purchase all the gears independently. Maybe we could look into buying a long metal gear stock and see if the different teams can utilize just 2 or 3 sizes even. Yeah, I think in my previous experience, like once we have a good idea of that specific printer and the characteristics, we can easily make some sort of just shrink ratio when we set to print it. In my experience, it matched relatively okay, and the wear on the teeth is okay. But yeah, we'll have to actually print out the gearbox and test it out.
By the way, I have an unrelated thought, completely, well, touched on tangential to the gears, but I'm looking at the two arms that you have that hold each of the launchers, and it looks like they would interfere with one another. Like if they were to try and cross each other's path, like one actually has to rotate like 360 degrees in order to get around to the next correct clocking. Is that true or not? Or am I just not looking at the model correctly?
Yeah, so we are already aware of like the interference with the gears, but we this is kind of like a little rush at the end. A lot of this integration happened in the past like week. So there was a lot of, we were already aware with a lot of problems that we didn't talk about during the design review. But currently, we are not going to be rotating arms 360 degrees. It's only going to be about like maximum, plus or minus 30 degrees. So we're going to be trying to make the gears smaller on the arms and then eliminate some of that ribbing you see on the height of the arms so that we can accommodate for what you're.
I'm not talking about the gears interfering.
The arm, right?
Yeah, I'm looking at how the arms interfere with them.
This was one of the design decisions that we made, I believe, in fall quarter, where we were concerned about the entire balance of the robot when it was hanging from like a single cable from the ceiling. So we wanted to make sure that the connection point to the robot was exactly at the center of mass. So you could see that these launchers are aligned exactly in the middle of the robot. So in order to do this, like you said, that means that these two launchers needs to be aligned along the same like plane. So we can't have them like pass through each other when it wants to control each of the angles. So we ended up figuring that using the yaw rotation control part that our sub-team is working on, we would have the robot rotate 180 degrees all the way around to do the next launch. Do you kind of see what we're talking about?
Yeah, but if you're doing that, then why do you need the arms to rotate at all? Couldn't you just have them at a fixed angle apart from one another, shoot one, yaw around, shoot the other, and then just yaw around?
I think
like it seems like like you don't need the arms to move at that point.
I think we were still considering that we wanted to shoot different attack angles, should we say?
Yeah, I mean that's a totally legitimate decision. Right. I mean, so props to that.
I think that was the reason behind why we kept the ability to angle the launcher.
Okay. And then with regards to your cable reel, I noticed that the hole coming out the center of the cable reel for the cable, that had a sharp edge, and even if it's not going to overstress your shaft, you're still going to put a nice pinch in the no, not that. There was an FEA slide, I think one of the first years presented. Yeah, that right there. That's gonna fray the cable and pinch it. You're gonna want to round that off.
Oh yeah. As you can see in the first picture, it's not a sharp edge. Maybe hard to see, but that part is filleted.
Okay. All in all, I mean, I'd like to say you guys have done a really fantastic job of letting the math define your, like, starting from basic requirements and then deriving your individual subcomponent performance from mathematics. That's something that, a lot of other teams either don't do or they're not really in a position to do because their requirements are so dynamic. Combat robots is a good example of that. But I think you've done it really well here.
Thank you. That's very nice to hear. We like to hear that we're going about things in the right way because sometimes we feel very adrift in this process. So thanks for that.
But then, sorry to dominate the conversation, but on that line, you guys have done a lot of FEA, and that's good. And I'm looking at the way your FEA seems to be set up, and it seems to be reasonably good. The only thing I would caution you on is your stress allowables when you're saying you've got a factor of safety of, X. You need to be derating that and using a lower stress, like max stress allowable, instead of 45. I forget whether it's 45 megapascals or 45 KSI. But whatever your number is, needs to account for the fact that 3D printed ABS is significantly weaker than solid ABS. You're gonna be breaking along the weld lines from each successive layer. You're not gonna be, it's not gonna be necking like a traditional solid material would. And what that, that might drop your tensile stress of the ABS by, could be a factor of 2, it could be a factor of 6, it could be a factor of 10. I don't know what it is, but you need to figure what that number is. And then you also need to account for the fact that unless you're 3D printing these at full 100% infill, the stresses that you're getting in your FEA are, you're running it as if it was at full infill, so you need to be printing it that way as well.
Yeah, I realize we didn't notate that on the slide as much as we should have. One of the things that we touched on in past years of X1 is planning to 3D print all our parts and then saying, oh, well, if it's 3D printed, the FEA is not going to be accurate. So then we didn't run enough FEA. And we got criticism for that. So yeah, I would say that all the FEA that you see is important mostly to show things like just the overall plots instead of actual numerically showing where the stress concentrations are. But yeah, I would definitely encourage all my teams to take those numbers with a grain of salt.
Yeah, another thing I wanted to note is we knew that we had to downgrade the factor of safety, but we don't know how to go about finding how much to kind of lower our maximum stress yield by. It's really hard to, because it depends on a lot of things like, sorry, I think I cut out there. It depends on a lot of things like infill, layer height. There's a lot of factors that go into it, and we don't know where to start when kind of deciding on how much to downgrade the FOS by. And yeah, if we have to do it empirically, that'd be really tough.
So I'm just Googling this real quick right here. And like I just Googled 3D printed tensile strength of 3D printed ABS. And you're right. It may be it's going to be extremely difficult to find good numbers. And in fact, what you'll probably find out is that no one's numbers that you find online are going to be representative of what your exact situation is. This is one of the reasons why, like, tensile, there are industries that build tensile testing machines brand new, and people still buy them and people still use them because there's an infinite need for tensile testing, because if you were doing this at a company, you would have to do the tensile testing yourself and determine what that cutoff is. A good way to probably work around that is just try and find several different examples of people who have done this testing online. You might find some hobbyist that says, oh, it dropped my tensile strength by a factor of 3, or oh, my tensile strength was 25, KSI or whatever it was, and just use the lowest number that you find. And it might be right, it might be wrong, but at the very least, you can't say you're not being conservative.
Right, that's a good start. Thank you.
Hello, can you guys hear me?
Yeah.
Yeah, hi.
Okay, cool. Hi, I'm Josh. I'm really impressed by all this analysis. I wish my senior design project was this thorough. We kind of did this with an electromagnet and a launcher and a reel and everything, and it didn't work. So could you go back to that slide with the the launcher, one of the launcher slides, like for pulling back the electromagnet. No, the one with the math. The motor math.
Okay.
Because I think I noticed, I'm wondering, is the stall torque, is it the stall torque that's 1 Newton meter?
Yeah, so the stall torque is actually higher, but on the website we're buying it from, they're suggesting the operating torque to be 1 Newton meter, which is which is why we chose it, because that would be a safer option.
Okay, yeah, I was just concerned about that.
Yeah, no problem.
And do you have the electromagnet already, right? Like, I remember I saw someone was like using a force like gauge thing.
Yes, I do. Yeah.
Okay. Have you tried like throwing it at things and seeing if it sticks?
Yeah, there's no way I could quantify that, but I tried, and the results I got were that we had to be very significantly close to the material before anything happened. Kind of in line with what you said last time with the design review.
Yeah. But I do like the design of like the holder. But for the holder of it, I noticed it's like perfectly sized, and I feel like you'll have to bend the wire a lot, because, or at least the electromagnet that I bought from Amazon, like the motor was sticking out the side. Are you able to get like space in the holder for the cable of the electromagnet?
Yeah, that's an adaptation. Originally we had an electromagnet that had the wire come out of the bottom, and basically for budget reasons, we decided to switch to a different electromagnet. The wire comes up the side, so we might just have to notch out a little bit.
Okay.
So that'll have to see once we actually have the parts in hand, I think, too. So
okay, nice. Let me see. Oh yeah, what's like the release? Was it the partial gear?
Yeah, so we thought about this, and yeah, so that's why both the gearboxes have partial gears in them, because we needed we needed to launch the spring, and we needed the reel to stop locking up the cable. Yeah, so that's our release system, because we didn't want to have like a actuated dog gear or anything in our gearbox.
Yeah, no, I like that idea a lot. We did like a release thing, and it was very scary when it wouldn't release, and we had to do it by
so
hand.
for us, I think the biggest thing is like we did do a FEA, right? But like we just need to see if it like actually works or not. If it doesn't work, we have to try to step up to like a stronger material.
And so that gear is like that has to be, I think, the strongest part of the whole robot. I'm pretty confident that everything else is gonna work. It's just like the launcher itself. You're like, if the spring's really strong and shoots the thing, is that gonna be a metal gear? Like at least that one gear?
Yeah, but like it doesn't. So I thought about if I can just use that, have that one to be metal, but the load, like, can you go to a slide where it shows the gearbox?
Yeah, I'm trying to find
with
one.
the gears.
Is it after this? It's going to be before this, right?
I think it's like previously in one of the gearbox. Okay, sure, this one. Yeah, so say like I use one of the gears to be metal, but so the gear it's contacting also needs to be metal as well, because like if I'm simulating all the force on one of the teeth on one of the gear, that's like the same thing for the gear it's contacting. And we're like, since there's like two sets of the motors on both sides, we're like very poor. So, but we'll want to try this out first to see if it works.
That's true.
I agree with Josh. I think those teeth are going to get a lot of force. I also see what you're saying, or those are going to, you can't just have those get the force. But that ultimately goes back to your motor, right? So you have to make sure that your motor isn't gonna is going to be able to take that force as well, not only from it turning, but you're going to be using it as a brake. So
we calculated the motor to be like strong enough to be like, say like once we attach onto the ceiling, we can use the motor to like pull the robot up as well. So it's not,
okay.
that's why there's an additional factor of safety on the gearbox to make sure we have that, even though like if we're not at the peak of the torque curve or something for the motor.
Yeah, you're gonna have to use it to pull up, but I think there's gonna be, I think there's a potential for more force during impulses. Like when, I guess is that good? I'm not sure. So I'm thinking about it. I'm not sure if it's actually gonna happen. I think we're just gonna have to build this and see and figure out what happens.
Is this the biggest tooth size you can do?
So like, I think if it's possible, I thought about just making the gear wider, right? Which would just give me more area to distribute the force. But like, as you can see, the robot is already like really wide. We're already like actually like way over our initial design constraint. So that's why the gearbox are like pretty packed. If it doesn't work, I could just make the
like fewer smaller teeth or fewer big teeth.
Oh, I see what you mean. I think
bunch of small
this is a. I forgot the.
Like if you're making the gear,
Mhm.
just use like gigantic teeth.
Yeah, I see what you're saying.
Yeah, I don't know if you picked a certain size for if you have some rationale behind the size you picked, or if this was the default, but you
Yeah, it
want
was
the biggest tooth size.
it was in the beginning. Like I thought maybe it could be metal, so that was kind of the size. That was just kind of standard. It wasn't. It was just like a standard, pretty like module 1 gear size. But yeah, we could look into if we have room in the chassis space to just make all the gears bigger.
Okay, cool. Good job, guys. It's I wish I had an army of people at my senior design project.
A quick question for this launcher. What do you? It looks like you've got. I guess what are you doing to keep it radially aligned? You've got these 2 screws poking out the side that kind of allow it to. I mean, they don't seem like they keep it straight in the track. Like it could slop sideways or rotate along the axis that the screws form.
Sorry, are you worried that like the long screw that goes through could bind, or?
Well, I'm just like, I don't see anything that's holding the you've got this center block which holds your rack, and I don't see anything keeping that concentric to the outer shell.
Okay, yeah. So I think she touched on it a little bit, but maybe a little quick. You're right that it might not be perfectly concentric, and in our design, we thought that would be okay. The spring, we made cutouts at the bottom of that inner barrel, so we can kind of just, when we get the spring, we can just like twist the barrel onto it, and that's the same case for that's how the spring attaches to the bottom plate as well. So we hopefully like that will help keep it relatively concentric, but it could still tilt a little bit. But yeah, we didn't want to make it a really tight fit with inside, because that would add a lot more friction when we're trying to launch. So we thought as long as it transport the force directly from the spring onto the magnet is launching, that would be okay.
So for what it's worth, that rack needs to be held tightly against the pinion that's driving it. So you're going to need something to brace it. Keep in mind that, you know, if you've got something that's got like, I don't know what pressure angle your gears are, but say it's like a 20-degree pressure angle on your gear teeth, then that means you've got, you know, sine of 20 degrees times whatever spring force you have that's trying to push your rack off the pinion and prematurely launch. So you will need something to brace it in, you know, in the axis that pushes the rack into the pinion.
Yeah. Like Josh said, yeah, we could. Yeah, thank you for bringing that up. We could add some sort of just like back plate or a bearing on like the backside of that barrel.
Yeah, I'm looking at it. It looks like maybe if you think about a couple of really thin vertical, almost fins that are sticking out from that outer wall. So it's holding it in a couple of points so that it can't push back against that wall, but it's thin enough that it's not providing like a large area contact, something like that. A bearing is ideal because then it's very little friction, but the vertical, having a long vertical wall to keep it pushed in all points except for just one.
Yeah,
think about
well,
stuff
you
like
need
that.
two, but you could also do those reverse and put them in the piece that's connecting with the pinion itself. I mean, with the rack itself.
Yeah, that's true. You could put them going outwards.
Yeah. I mean, we could, yeah, like you guys said, we could just have two bearings that's like sticking out from the backside of the inner barrel, which will also ensure there's like barely any friction when we're launching. But yeah,
I don't think a bearing is such a good idea because although it's going to be less friction, you're essentially going to need 4 to make sure it's balanced up and down. If you only had 2, it could still slide over the axis, and if you either way that they're aligned. I think that having long, thin pieces like Rebecca's suggesting is going to be much more effective, even if it does cause a bit more friction.
Okay, yeah, we could have like some sort of like just 2 fins, or something like that, on the back too. Yeah, we'll look into it. Just 2 like extra printed fins on the back.
You have the screws that hold the top set of screws that hold in the rack also protrude out of the cylinder, so you kind of have like 2 points constraining it.
Yeah, so that is our like hope, but I'm not sure exactly like if the tolerances in those slots and the screws will like ensure it doesn't like wiggle at all. I think we could use like maybe we can just add like an extra safety in the back to make sure it doesn't prematurely launch.
Yeah, those are really good notes. Yeah, definitely something in the back because the force from the gear is going to push it backwards instead of forwards. Yeah, I'm going to keep going with comments. I know it's getting a bit late, but anyone who wants to stick around and give us more feedback is welcome to.
I saw that the Electromagnet mentioned something about using a paracord for the tether instead, so like to take the force off of the wire. If you consider like how much slack you would need in the wire, because I'm pretty, if I recall correctly, paracord stretches like a lot when it's under tension.
Yeah, so that's something we're definitely thinking about. Yeah, the idea was to create a significant amount of slack in the current carrying wire, as we call it, which should be threaded inside. I guess the degree to which the slack needs to be, essentially how much slack we need to have kind of depends on it so far, and we don't really have a definitive answer. I think we'll have to maybe look at it and test with the material once we have it. So, but yeah, thank you for bringing that up. Yeah.
All right, it's good to hear that you're thinking about it.
Mm-hmm.
I have a few rapid fire things and one kind of main thing. I'll start off with the faster ones just for sake of time. Have you considered, so you were saying, Hayato, that you wanted to get IMUs on the electromagnet parts, right, that attach? Are you worried at all about interference between the electromagnet and the IMU itself?
Are you talking about on the electromagnet or?
On the electromagnet, right? I remember you guys, or did I misunderstand?
So I think I didn't explain it well. We're just going to use the same IMU that we're going to use for the main body. So we're only going to have a single IMU on board. And how the mechanism is going to work is that whenever it launches the electromagnet and if it actually attaches to the ceiling, whenever it reels in the wire for that newly attached electromagnet, it should move the body towards the ceiling. So we were thinking that we could possibly detect that motion to see whether or not it attached. Since if it didn't attach and if it's just dangling like downwards, then if you just reel in the wire, then all it will do is just bring the electromagnet back up.
Okay, my only concern with that would be in terms of, feedback and figuring out what exactly is going on, because
right,
your IMU might pick up, let's say you're swinging, it might pick that up instead of a connection and you reeling, or if you shoot up your electromagnet and let's say it just misses the ceiling and just falls, that might induce some kind of movement, and then your robot goes, hey, look, I've docked.
Right.
So I'd say I would suggest maybe having another concrete way of determining whether you've locked onto the ceiling or not, but obviously I know that complicates it, and you did touch on that. So
Right.
I guess that's just kind of more of a concern than anything else.
I think we were also thinking about how once it attaches, that means it'll be attached at like 2 points. So that would define a line, right? So then it would be like the oscillations that the system would have would only be in one direction. So if we could see that through our IMU, I thought that could be a way that we could see that it's definitely attached at 2 points. Since if it's only dangling from a single point, then the oscillation patterns would be different.
Okay.
It'll
And
be in
so
2 dimensions.
I guess is the idea then, if you, let's say you misfire and you don't actually, or I guess not misfire, but you don't actually connect to the ceiling and you start reeling in and then your IMU is like, hey, I'm not moving, is the idea just to kind of reset and try again?
Yeah.
I guess. Okay.
I guess, yeah, you could say that. Since
Okay.
either way, we are going to reel in the motors since it's fully extended. So we would want to bring it back to like a medium position so that it could prepare for the next launch. So it is in the process, like in the launching process, that we would want to reel it in. So we were
Right.
just going to take advantage of that and then see if we could detect the attachment through that method.
Cool. All right, just to keep going down my list, I guess the other kind of big thing that luckily Tim also mentioned in the chat is reeling it in and making sure it actually returns to the proper position. I think that's going to be a huge thing, because if you disconnect from the ceiling, ever so slightly too soon, you have this giant thing falling from this, just free falling, and then you're reeling it in while it's falling. That might mess with some things. So I'd say maybe put some more emphasis on making sure that you can reel in correctly and make sure that it realigns ready for the next launch. And then what else is there? Could you, so I noticed that you were doing double bearings. One of the earlier slides for, I think it was the slip ring slide, maybe slide 13. I think I tried to remember the number. I think it's 13, but oh no, I was wrong. Very wrong.
It's in the ARC chassis.
Yeah, then maybe was
Axle, I
it
believe.
31 then? Am I? Yeah, I was close. It's 31, not 13. I noticed the double bearing and I was wondering if you could clarify why, because that seems like unnecessary weight to me.
Nick, do you want me to, or do you want?
Yeah, you go ahead, Riley.
All right. It's mostly just for a larger surface area, so you have more force distributed along it. So if you only had like the space of one bearing, I think it's like, I don't even know, I forget what the number is, but the thickness of that, and you only have, if you have like all your weight on that spot, it's not as good for the 3D printed part that we made. So then we
Okay.
put 2 in there just so it has more space to both stay on the reel and for the reel to transport the force to the rest of the structure.
Okay, I would recommend either looking into a bushing or a wider bearing, just because those two are still independent of one another. So you can get independent rotation for each of those, which might do you more harm than good. That would be my suggestion for that.
Yeah, I'd say look into a bushing for this.
Yeah, just so you can get a wider surface.
I forgot about that.
We always forget about them. And honestly, for the RPM that you're gonna have here, there isn't much of a need for a ball bearing. At least in my experience, this is what I've found.
Okay. Yeah. Thank you.
Cool. I guess the last rapid fire thing is that just to reiterate the whole 3D printing thing that I know we've been kind of drilling at this point, and I'm sorry. But just like previously mentioned, make sure everything prints correctly and also use that as a grain of salt for all your FEA. Don't want to drive that point too hard because we've already talked about it. My main concern was, would you mind pulling up the complete CAD really quickly to the slide of it? I'm struggling to see that kind of central hex axle and how that's fully functioning. So okay, so you have the arm, you have a servo that controls the arm, correct? And then you have your DC motor hooked up to your gearbox, and that's doing your reeling, right? Am I understanding that correctly?
Yes.
Okay. So does the gearbox and the DC motor that controls your reeling, is that attached to the same axle as the arm? So are those rotating together?
There's a bearing in the arm. It's a hex axle bearing. So anything that's a hex axle will rotate along with the reel. But since there's a bearing with the arm will be able to rotate independently from the reel. If that makes
Okay,
sense.
so the arm is completely independent, the servo is moving that, and then the reel is also independent. It's rotating with the hex axle.
Yeah.
Okay, then I guess two things there. I think it would be ideal if you can get the arm and your reel to rotate together, just because you might have a situation where you have some like slot or slack tension, because let's say the last point on your reel is like pointing straight up, but then your arm is not aligned with that, so then your wire kind of does a weird thing and maybe tugs on your motor. If I'm being able to explain this correctly, that's something that kind of worries me, and I think it might hurt your launch of your electromagnet, since that tugging might misdirect it.
Yeah,
if I'm making sense.
I think I get what you're saying, of just the arm moving back and forth is going to wind or unwind the cable a little. Is that what you?
Exactly, yeah, and it might kind of mess up with how your reel is doing. So I see you have those little, I'm assuming 3D printed C-clamp looking things at the very base of it that hold your gearbox stationary, which tells me that well, see that's what I'm kind of confused about. So you have that gearbox driving what, a gear that's on the hex axle and that's attached to the reel, correct?
Yeah.
Okay. Yeah, I'd see if there's any way that you can get those to combine into one unit where you have the arm and that gearbox and that motor, and maybe that can save you the whole counterweight situation that you have currently with the arms. Instead of slapping some kind of steel useless part on the end of it that's giving you useless weight, I'd say maybe see if you can work with that gearbox, maybe elongate it so that you get more weight further away from that central rotation axis, and that way you don't have dead weight, you have actual weight that you're using, counteract. Plus
so are
that
you
would kind of
recommending us like basically mounting the reeling gearbox onto the arm, right?
I think personally I would, just because I'm concerned that if your arm is not correctly positioned with your reel, then you're going to tug on it, right? And then that's going to, when you try to launch your electromagnet, that tugging is going to play with it, and I have a feeling it's going to shoot short every time.
I definitely see your point for the counterweight. I think that's a good point. But for your second point of concern, so the partial gear design, which like it helps us. So once we've reeled in the electromagnet, the reeler should that partial gear should stay in the point of no, like it doesn't contact. So whether like the arm moves or not prior to launching, it wouldn't interfere with anything because the wire is just free.
Yeah, there's
at
a lot
that
of
stage.
slack in it at that point.
Oh, I see. So, okay. So then your actual reeling is done also as well by a partial gear. So you're
Yeah.
not full. Okay. Um. Yeah. I guess that would do it then
Yeah,
if
it's kind of
you're
tricky.
free spinning it.
I mean, it's ideal to have the reel move when the launcher arm moves, but you can't get over the fact that the reel has to move when the launcher arm isn't moving. Right. So you can't directly link those two motions together.
But yeah, but like if you, like he said, if you just mount the reeling mechanism like on the arm, it's like
Yeah, I agree with that. No, I think that could be feasible. Just, at first glance.
No, I mean,
Yeah.
this is more of like a nitpick thing that I just wanted to make sure I understand the design correctly because it's a complicated thing. This is really badass. As everyone has been saying, this is killer. I'm like super proud of all of this. This is ridiculous. So yeah, as former X1, this is making me super proud. Y'all killing it. I'm jealous.
Thank you. Thank you.
Oh yeah, I wanted to say something about I'm really proud of you guys. This is really cool. And it really shows that you guys put all the you guys used all of your knowledge in this. And all of our criticism is just things that we learned from experience that you guys just don't you can't have, or you haven't had yet. And especially with not having the lab and not being able to actually do this stuff, it's super impressive how much you guys have already accomplished.
Yeah.
And I I never know how to end these. Yeah, no, really cool job. This team and the BruinBot. Hayato said he's guilty for pitching a really ambitious project, but I think if it weren't for COVID, you guys would be already testing stuff out and making all these changes that we've already been talking about. So it's this is definitely
That's the hope,
your
yeah.
skill.
A lot
Yeah.
of what's missing from this process is the prototyping and just getting the physical intuition that we don't have, that a lot of you have and are helpfully directing us about things. So we do appreciate that. But yeah, not being able to do things in person has been really rough. But yeah, I think the progress all the teams have made has just blown me away. So thank you guys. I realize I'm still recording this. I probably should have stopped a while ago because this is gonna take a long time to upload. But
Are there any other comments or
Yeah.
questions just as a final round, I guess?
people who are reviewing the video materials later, so I wanted to make sure that we got the feedback in case any of them had the same questions. So I'm gonna stop the recording here, but we can keep going if we want. Will it let me? There we go.